Hello, 20-2 students. So today we're going to be looking at the cosine law. So remembering last lesson we looked at the sine law. So we're expanding on that a little bit. Now for this lesson I have combined section 3.3 and 3.4 from your textbook because 3.4 is basically just applying all of these things that you've learned to kind of more complex problems. So we'll look at that in this lesson. Okay, so first of all, looking again at oblique triangles, a second law that can be used is the cosine law. And so when would we use this? Well, we do that when we have information on two sides and the included angle. So basically what that means is you have two sides, like let's say A and C here, and then the angle in between. Let's see. Maybe I can apply that better for this one. So if we use this, there's different versions of the sine law that the cosine law that you will find, which I've written down over here. But this is the one that's on your formula sheet. So here's the formula sheet you can use on tests. And so this one would be the one that you'll see, and we'll look at how you can manipulate it depending on the sides of the triangle, but basically for this one, if you were looking for side A, so this side for example, you would have to know side B and side C, and then like I said, the included angle. So what's the angle between those two sides? It's angle A, and you can see that in this formula, right? That you would have to have your known sides B and C. You use the same values here, and then you have to have the angle A. Okay, there is an alternative version of this that's the cosine law that's used to find the angle. This is also on your data sheet that you will have on tests. And again, like the other one, we can manipulate this one around depending on the sides that we know, but we'll talk about that as we kind of move forward. So with this one, if you're looking for angle A, so this angle, then you would have to have sides B and C and side A. Okay, so in this case, you need to have three different sides known in order to solve for the angle that's between those first two. Let's see. So, and then, yeah, like I mentioned, that the law can be written in terms of any side. Basically, you just have to rearrange. So if we look at this first example here, this is the original version. If you were looking for side B, basically all you would do is think about your original one, and you're basically just swapping them out, right? So if you're looking for side B now, instead of a squared being on this side of the equal sign, you're going to have b squared, and then instead of b squared here, you'll have a squared, so you're just swapping them out. And then same thing here, you would normally have bc, but now you're going to have ac, and then the other thing you have to consider is that because you need to have the included angle for the two sides that you're dealing with on this side of the equation, so this time you're looking at sides A and C, now you're going to have cosine of angle B. So it's always going to be cosine of the angle that is opposite the side that you're looking for. Okay, and then of course you can do the same thing if you were looking for side C. Now you would have a squared plus b squared, so basically the other two sides here, the other two sides here, and then the angle between those two sides. So between A and B we have angle C. Okay. All right, so let's go into looking at how we can use this law. So we'll start out with a nice straightforward example. And we'll go from there. Oh, sorry, one thing to mention too, this is written on the filled in notes, but these variations are not going to be on your formula sheet. So you do have to know how to work with the original one to manipulate it for any triangle that you want to work with. So in this question, we have a triangle and we're looking to find the measure of side x. Okay, so they've labeled, we have angle A, B, and C. So let's maybe label the sides properly. So across from angle C, we're going to have side C. Across from angle B, we're going to have side B. And across from angle A, we're going to have side A, which is what they've labeled as X. So basically, when we look at the triangle, we should be looking for whether or not it satisfies the rules for the cosine law. And because we have two sides and an angle in between them, it does. And so we can go ahead and work with that to solve for A. Now the nice thing is this one already has everything set up for the formula in the version that's given on our sheet, because we're looking for side A, and it's going to be equal to side B squared, which is 10 squared, plus side C squared, 12 squared, minus 2 times by side B, which was 10, times by side C, which was 12, times by cosine of angle A, which is 62 degrees. So we're basically just filling in numbers. So if we expand that out, we're going to have 100 plus 144 minus, now if you multiply all of this out, just keep in mind, depending on the calculator you're using, just make sure you're doing your order of operations carefully. So for me personally, I would do the cosine 62 first. And then I like to just hit enter. It shouldn't matter if you close the bracket, but if you don't close the bracket and you start multiplying things through, you will get the wrong answer. So cosine 62 times by 12 times by 10 times by 2 gives me 112.67, some kind of an extended decimal there. So I'll just show you what I meant of how you would get the wrong number. So if you do cosine 62 times by 12 times by 10 times by 2, you get negative a half. And the reason for that is if you haven't closed this bracket, then the calculator thinks you're asking what is cosine of 62 times 12 times 10 times 2, and that's not what you're looking for. You're looking for cosine of 62, which gives you a decimal, times by 12 times by 10 times by 2. So just make sure you're aware when you multiply through, you need to make sure you close the bracket on the angle there. Okay, so 100 plus 144 minus 112 gives us 131.326. And so that's our A squared value. So remember, just like with Pythagoras, when you have something equal to a squared value, you want to square root it so that you can solve for the actual A value, because basically that means we're square rooting this. So now we have A is equal to, and if you square root, let's see here, 244 minus the 112. So if you square root that 131, you end up with 11.459. Now we'll keep it, because these are all just whole numbers, let's keep it as a whole number. So with the 4 there, we don't have to worry about rounding, so we can say A is equal to 11 centimeters. Okay. So that's a really basic version of the cosine law. Now we're going to look at something a little more complex. So it says, using the diagram to the right, find all missing angle measures. Okay, so we have multiple different sides, but we don't have any angles. So let's start out and see if we can use the first kind of law here, or the first formula here for solving for angles. And what I mean by first is just like the one that we're given, not where we're trying to manipulate it to solve for another one. So for cosine of angle A, we'd be looking for this angle here. So let's maybe put that in so we can keep track. So if we have cosine of angle A, we would need to have side B. So let's maybe label our sides first. And I recommend that you always label your sides, because it's really easy to lose track of what's what if you're not paying close attention, and especially if you're on a test or like under a little bit of stress, it's easy to kind of lose track. So it's best to just label everything before you start, and then you don't have to worry about kind of losing track of stuff. So okay, so we have our sides. So what we're going to have is b squared c squared minus a squared over 2 times bc. So we have all of those number values, so we know we can solve for angle A. So now we just have to plug in the numbers for that. So cosine of angle A is equal to b squared, so 15.2 squared. Whoops. I'm squaring too soon. Let me just grab my whiteout there. 15.2 squared. So b squared plus c squared, which is 7.4 squared, minus a squared, so minus 11.6 squared. And then we need to divide out 2 times by b times by c. So 2 times b, which is 15.2, times by c, which was 7.4. Okay, and so if you do all the math for that, again, just be careful with your order of operations in your calculator. So you might want to go through, put in the calculations, make sure you get 0.672 as your answer for that one, and then you know that you're on track with how you do your order of operations. Okay, so now clearly, like I've mentioned before, if you get an angle that is less than 1, then it's like a good reminder to you that you probably are not on the right track, because generally we don't have angles that are that small. So what does that tell us? Well, just like with any trig function, if we have cosine of a is equal to a number, then we still need to solve for just a. And the way that we do that is by algebraically moving cosine away from the a, so we just get the angle. And what that basically means is that we're doing the inverse of cosine. So we're doing cosine minus 1 of 0.672. And when we put that in, we end up with 48 degrees if we round off. Okay, so I'm just going to use whole numbers for my angles here. On a test, if it's not told to you how many decimal places, like if you were to have 48 here, that should be fine. Usually, because I'm more based actually in the sciences, is what I normally teach, I kind of always think about significant digits, which if you're familiar with, it would be like the most number of digits that we have in our given data is what we would limit our answer to. But if you don't know about that, then don't stress out too much about that. With math, I don't think they concern themselves quite as much with that. Okay, so now we have angle A here is 48 degrees. So we still need to solve for two other angles. So let's try looking at angle B here. So what we want to think about is how do we kind of change the given formula in order to solve for a different angle. So with that, in this case, we're going to be looking for cosine of b. So let's write that out and then think about how that would have to change. So if cosine of b is equal to b squared plus c squared minus a squared, and we're looking for angle b now, basically we want to swap out the corresponding sides. Okay, so what that means is instead of b squared here, which we had when we were solving for a, now we want to have a squared there. Okay, so a squared, c squared is going to stay the same, but we're swapping again because we're solving for angle b. Instead of minus a squared, we're going to have minus b squared. Right? So just making sure that everything is taking the place properly. And then we want to divide it by 2. And previously we were looking for BC, but because we're dealing with angle B now, we want to change that to AC. Okay, so that's how you swap it out. And so now we can just plug in our numbers. So a squared was 11.6 plus c squared is 7.4 squared minus b squared, which was 15.2 squared. I don't know why I keep doing that. 15.2 squared. Okay. And then I want to divide that by 2 times by my a value, 11.6, times by my c value, which is 7.4. Okay, and so again, I'm going to get cosine b is equal to a decimal, right? So in this case, it's negative 0.24. And so if I want to isolate b again, I need to do b is equal to cosine minus 1 of the negative 0.24. And that gives me 104 degrees. So again, I'm just going to keep it as one number. And if we look at this triangle, I mean, I know we can't always do that because often these are not drawn to scale, but it looks like it would be a bigger angle here, so it seems fairly reasonable. Now for the third angle, this is always the best part, is once we have two other angles, we know that all we have to do is 180 minus the other angles we found, 104 minus 48. And that leaves us with 28 degrees, which again, we don't want to rely too heavily on this because these usually aren't drawn to scale, but it does look like it would be a narrower angle, right? So that seems good. All right. So consider the following information. We want to look at how do we solve problems when we're not given a triangle drawn out. So in this one it says, consider the following information. Angle A is equal to 36 degrees, AB equals 3 centimeters, and AC equals 6 centimeters. So we want to find side A. So often with these, I mean, you can kind of try and get a sense of it. Like if AB is 3 and AC is 6, it's going to be bigger, but honestly, I usually don't actually try too hard to keep it to scale because it can be kind of tricky. Okay, so we have, let's just label it ABC. Okay, so angle A is going to be 36, so this is one thing we're given here. Side AB is going to be 3 centimeters, and side AC is going to be 6. So we can see that I definitely did not come close to drawing that to scale. And we want to solve for side A. Okay, so as it turns out with this drawn that way, we are set up to use this is kind of, I can't really put this in a good way, but we're set up to use our cosine law here, right? Because we're looking for side A. So the cosine law is A squared equals B squared plus C squared minus 2BC cosine A. Okay, so now we can just plug in our numbers. So B squared, oh, sorry, and that's one thing I forgot. We should always be labeling these. So C is 3. Okay, so B squared is 6 squared plus C squared is 3 squared minus 2 times by 6 times by 3 times by cosine of angle A, which is 36. And so if we get that all out, we're going to end up with 15.875. Again, try this in your calculator to make sure you're getting the right answer so you know all your order of operations and the way you're working with your calculator is proper, because you don't want to figure that out by doing a test and getting the wrong answers. You want to know now how your specific calculator needs things to be put in. Okay, so we're just going to square root those, so we're left with just the answer for A. And when we square root 15.875, it's almost 16, so we're going to get 3.9 something, and we're going to round that to 4 centimeters. And looking at this triangle, that seems like a reasonable value, right? So that's another thing to always do at the end of your questions is like if we would have suddenly had, you know, like 50 centimeters here or something, we might have wanted to like take a quick look at our calculations because that would seem disproportionately large. Okay. Let's look at some word problems. So this is something that you are definitely going to run into. So you want to really like work to develop your skills of working with word problems, because one of the main things that I find students struggle with in these types of questions is visualizing things. So you have to be able to read the question and kind of like sketch the diagram to match with it so that you really, you know, have a good sense of how the numbers are set up. So in this one, it says 2 airplanes leave Hay River Airport in the Northwest Territories at the same time. So I'm going to kind of like make a little starting point here. The 2 airplanes are going to leave at the same time. Now, just to read the question really quickly, one airplane travels at one speed, the other one travels at another speed. About 2 hours later, they're 800 kilometers apart, and we want to figure out the angle between their paths. So we know that they're heading in different directions. And we know that at some point in time they're going to be a certain distance apart. So what I would kind of draw is, okay, maybe one heads out kind of in this direction, maybe the other one heads out kind of the other direction. And then at some point they're going to be a certain distance apart. So, okay, so I can actually start applying some of these numbers. So this is going to be like where they're at 2 hours later are these 2 points, and the distance between them is 800 kilometers. And we're looking for the angle between their paths. So we're looking for this angle here because that's the angle between how they're traveling. Now, a lot of students might kind of impulsively want to put in, okay, plane number 1 travels 355. So they might put in 355 here. So stop and think a second if that would be appropriate. Well, because we're looking at distance on this side, we can't put speed in on another side. So an important rule to keep in mind is that when you're building up these triangles, you should not ever have different units on different sides. Okay, so we can't say that this is 355 and that's 450 if we have a distance here. And the other thing you might be wondering is like, well, why couldn't we just do the 2 speeds and not the distance? But well, what you have to keep in mind is that the speeds are not going to represent anything about how they are related to each other in space, right? So, but distance will. So that's why we had to choose that one as the distance on this side as our number value. And so the other thing that we now know then is that for these sides, we do need to know distance. Can we figure out how far something has traveled if we know how fast it's traveling and how long it travels for? Well, yes, right? So if they travel 355 kilometers per hour, remember that means that in 1 hour, they travel 355 kilometers. So after 2 hours, you're going to have, so let's do plane number 1 is going to be traveling for 2 hours times by 355 kilometers per hour. Okay, and even like if you're familiar with conversion factors at all from any of your sciences, you'll know that when we multiply hours times by kilometers per hour, the hours cancel out just like any number being divided by itself, so you're left with your units. So you can always use units as a way to check whether you've done your math correctly. But I also obviously very strongly encourage you to just think about the logic of that, right? If you're going this fast in 1 hour, or this many kilometers in 1 hour, then in 2 hours you must do twice that. So we end up with 710 kilometers as the distance. So let's say that this side here is plane 1. Okay, and so we can fill in that distance on this triangle now, 710 kilometers. And then plane 2, same thing, 2 hours, but he's going 450 kilometers per hour. And so we end up with 900 kilometers as the distance traveled by that plane. 900 kilometers. Okay, so now we have our distances and we're looking for an angle. So we have 3 sides of the triangle and we're looking for an angle. So we know that, and this is where you can start thinking too a little bit about, like we've looked at the sine law already in this unit, and we have the cosine law, and then of course we have Pythagoras. So with Pythagoras, we cannot use it unless it's a right triangle, and we don't know that this is a right triangle, right? Like we kind of sketched it out. It could be because we don't know, because we haven't calculated anything in there, but always assume that you can't use the Pythagorean theorem unless you know for sure there's a right angle in there. Sine law, we can't use sine law because we would need to have at least one angle in order to use that. So all we're left with is using the cosine law because we're looking for an angle, and the only thing we have is sides, which is exactly what the cosine law gives us. So we're going to do, let's see, we want cosine of angle A, so let's call this angle A then. Okay, so the other thing you want to do is, unless you are really comfortable with rearranging, you want to set your triangle up so that it matches these rules. So if we have cosine of angle A, So angle A is going to be between sides B and side C. So let's make this side B, and oh, you know what? I'll keep it consistent with, it shouldn't really matter because it shouldn't really matter which side is C and which side is B, but I'll keep this one consistent with what I did on the filled in notes. So side C, side B. But it wouldn't have mattered really if you switched them, because basically all that means is we have side A, so side C is opposite angle C, side B is opposite angle B. Okay, so now we can just go ahead and start looking at plugging in our values, right? So it's going to be a cosine of angle A is going to be equal to B squared, so 900 squared, plus C squared, so plus 710 squared, minus A squared, so 800 squared. And we want to divide that by 2 times by B, which is 900, times by C, which is 710. And when we do that, we end up with 0.527. So again, you always, when you see that angle that's less than 1, you kind of are reminded that you need to do the inverse of cosine to solve for that. 0.527. And we end up with 58 degrees if we round it to a whole value. Okay, so if you were answering this on a written question on a test, you would just want to write out the angle between the planes is 58 degrees. Okay, all right, let's try one more, actually even more complex word problem, because this involves kind of like more than just the 2 dimensions. So Ryan is in a police helicopter 400 meters directly above the Sea to Sky highway near Whistler. Okay, so he's up here in this helicopter and he's directly above a highway. So we have a distance going down here to the highway, and that is 400 meters. When he looks to the north, the angle of depression to a car accident is 65 degrees. Okay, so let's say this one is north. So we have an accident over here on the highway. And when he looks to the south, so of course that's going to be the exact opposite direction, he sees that there's a approaching ambulance. Okay, so I'm going to maybe bump it out a little bit. So ambulance. Okay. And we're also given this information about an angle of depression. So this is something kind of important to be aware of because we've looked at angle of elevation. I'm just going to use a ruler so I don't totally botch this for you guys. So we've looked at angles of elevation, and I'll just kind of quickly illustrate this here. If you were talking about an angle of elevation, you'd be thinking, what is the angle between the surface that we're thinking of and the thing that we're looking up to? So this would be an example of an angle of elevation right here. When we're looking at angles of depression, it's a little bit more complex because you're basically thinking about an invisible horizontal line with wherever you're at. So this guy's up in this helicopter, and we're going to kind of imagine that there's this horizontal line, which is the horizon for him. An angle of depression is always the angle between that imaginary line and the line of sight down to whatever he's looking at. So this would be one angle of depression, and it's said that when he's looking at the accident, the angle of depression is 65 degrees. So this one's 65 degrees. When he looks to the south, the angle of depression to the ambulance is 30 degrees. So that's going to be between the horizon and the line of sight down to the ambulance. Okay. All right, so there's our drawing. And And let's see, what is the question asking? So how far away is the ambulance from the accident to the nearest tenth of a meter? So we're looking for this distance here. So let's call that side A so that it matches up nicely with our cosine law if we need that. So if this is side A, we're going to call this as angle A. And then I don't know, let's just do B and C, which would make this side B and this side C. Okay. Okay, so we want to solve for side A. Now this is a little bit tricky because if we were going to be using, for example, the sine law, then we would have to have one of the sides and another angle. And two other angles, sorry. So that could be tricky. Now with the cosine law, if we were looking for side A, we would need to have the two other sides and one angle. So again, we need more sides than we have. So we need to think about how we can solve for these two other sides. Now this is one of those cases where we're actually we have this weird other extra piece of information. We have this 400 meters. And because he's like straight above this point, and then there's things going on to either side, this is going to make the big triangle into two right triangles. And so what we actually have is one side of this triangle and one side of this triangle. And because we're given these angles of depression, we can solve for the angles inside of those two triangles so that we can solve for another side in each one of those individual triangles. So remember, that means you can't solve for A because A is a side of the two triangles combined, but we could solve for B in this triangle and C in this triangle. Okay, because we have a side, we'll get an angle, and we can solve for a second side in that case. So what you need to keep in mind then is, if you remember back to complementary and supplementary angles, if we have the line of sight here is supposed to be perfectly horizontal, and then the distance down is perfectly vertical. So this together forms a 90-degree angle. We have 30 degrees used up here, so in order to make it to 90 to come all the way down to the vertical line, we're going to have an angle of 60 degrees there. Okay, same thing on this side. We have 65 here, so to get to 90, we would need to have 25 degrees here. Okay, so now we have those two angles as well. Okay, so now we can go ahead and start looking at solving these two triangles. Now, because we have an angle and two sides, an angle and a side, and we want another side, what we can use is just classic trigonometry, right? And also the other factor in that is that we have a right triangle. So what we would need to think is, if we're trying to solve for this side here, we're using this as our reference angle, okay? And so which side is this and which side is this? Well, the reference angle that connects to a 90-degree angle is the adjacent side. And the side that's opposite the 90-degree angle in the triangle is the hypotenuse. So we have adjacent and hypotenuse. So remember, SOHCAHTOA is our kind of mnemonic to remember. If we have adjacent and hypotenuse, we're looking at using cosine. Okay, so cosine of our angle that we have, which was 60 degrees, is equal to our adjacent 400 divided by our hypotenuse, which is our unknown, so B. So now if we want to solve for B, we just need to move them around algebraically, so I'm not going to go through that, but basically we would have B is equal to 400 over cosine of 60, which gives us 800 meters. Okay, so just keeping in mind that if our units here were meters, we have to be consistent with that. Okay, and then what about in the other triangle? We basically have the same setup. So we're looking at this angle. We have the adjacent side that connects that angle that we're using to the 90-degree angle. And we are looking for the side that's opposite the 90-degree angle here. So that's going to be our hypotenuse again. So that means we're using the exact same piece of information here. So it's going to be cosine of, now in this case we have a different angle, 25 degrees, is equal to 400 over c. And so if we rearrange that, it's going to be c is equal to 400 over cosine 25. And that gives us 441.35 meters. So we don't get a nice even value for this one, but that's okay. So just make sure you keep your decimals through all of your calculations. So now that we know these two sides, and we also technically have angle A, right? Because we know that angle A in this big triangle is going to be these two combined. So that's going to be 85 degrees, right? So angle A equals 85 degrees. We have side C and side B, and we're looking for side A. So now if we look at our cosine law, if we have B and C and angle A, we can solve for side A. So now we can just start plugging in numbers. So A squared is equal to B squared, which we said was 800 squared, plus C squared, which was the 441.35 squared, minus 2 times by B times by C times by cosine of angle A. So that'd be cosine of angle A was 85 degrees. Okay, and that gives us 773,244.791. So just remember we need to square root both of those. So we end up with A being equal to 879. And we get a decimal, but they asked us to round to the nearest tenth of a meter, so we're going to round it to 1 decimal. So that's the distance between the accident and the ambulance, which seems like a reasonable number, right? We had 800 was this length, 441 was that length, so 879 seems like a reasonable length there. The next question asks us, if the ambulance is traveling at 80 kilometers per hour, how long will it take in seconds for the ambulance to reach the scene of the accident? So for part B, the first thing we need to think about is if they're giving us a speed in kilometers per hour, we kind of just talked about in the last question about how you can convert between speed and distance and time. But if you're traveling at 80 kilometers per hour and we want to figure out how long it's going to take to travel 879 meters, think about what would need to happen with these two values in order to be able to work with them together. Well, they always need to have the same units, right? So if this is in telling us how many kilometers you travel in an hour, we can't be thinking about how many meters there are. We have to think about how many kilometers they have to travel. So let's do a quick conversion here. So if we have 879.3 meters, then we want to multiply it by a conversion factor, which would be for every 1,000 meters. So again, remember when you're setting this up as a conversion factor, you always want to make sure that the units that you're trying to get rid of are on the bottom so that they divide out of each other. So times by, for every 1,000 meters, there's how many kilometers? 1 kilometer. Okay. Just trying to think if you guys have that on your formula sheet. You actually don't have that on your formula sheet, so you might want to make sure that you have like a little bit of an idea of how to do metric conversions. You would only ever be asked for basic ones like kilometers to meters is generally what you would see. So essentially what we find out is we have to do 879.3 divided by 1,000, which gives us 0.8793 kilometers is how far we're going. And that makes sense, right? Because 1,000 meters is a kilometer. So if we have less than 1,000 meters, we should have a little bit less than 1 kilometer. Okay, so now that we know the kilometers that they have to travel, we need to figure out how long it's going to take them going at that speed. So basically, if they're going 80 kilometers per hour, remember in the last one we talked about, then if you traveled for 2 hours, you would have to travel like twice, you would go 160 kilometers. In this case, we're thinking about distance and trying to get time. So what we would need to do again is 0.8793 kilometers. If we want to think about this as our distance, we want to figure out how much time it's going to take. I'm going to set up my speed as a conversion factor again. So what I want to find in the end is how many hours it takes. And what I know is kilometers. So I want my kilometers to cancel out. So I'm going to set up my speed like this. 80 kilometers in 1 hour is how fast they're traveling. So again, when I multiply, if the kilometers is on the bottom here, they're going to cancel out because they divide by each other to make 1. So essentially I'm doing 0.8793 times by 1 divided by 80, which gives me 0.010, and there's like an ongoing decimal there, but hours. So now if I have time in hours, they asked us for time in seconds, so now I just need to convert that. So again, using conversion factors, I'm going to say 0.010 hours times by how many, if you know how many seconds there are an hour, you can go straight to that. If not, you might have to do multiple steps. So you can look at the filled in notes to see if you're doing multiple steps. But basically there's 60 minutes in an hour and 60 seconds in a minute. So 60 times 60 gives us 3,600 seconds per hour. So again, always putting the units that you already had on the bottom there. So hours are going to cancel out. 0.010 times by 3,600 is going to give us 40 seconds is how long it's going to take the ambulance to get to the scene of the accident. And again, you might just want to really quickly think if that makes sense. So if the ambulance is going 80 kilometers in 1 hour, then how long would it take them to basically go 1 kilometer? Well, it's going to be a very short period of time, right? Under a minute. So that seems like a reasonable amount of time. All right, so those are kind of some more complex questions with cosine law. So go ahead and try some of these practice problems that are listed at the bottom of the notes, and then you can start working through the chapter review and getting ready for the test. So I will see you in the next unit.